All right, so now I'd like to show you how to use Ampere-Maxwell's law to derive an expression for magnetic field produced by the current, because what Ampere-Maxwell's law says that if we have current flowing somewhere, and it doesn't matter if it is conduction current or displacement current, this electric current induces magnetic field. So whenever we have current, we will have magnetic field. Let's take a look at the an example. So let's say that we have a straight wire and current flows in this wire. Let's now figure out what kind of magnetic field we would get from Ampere-Maxwell's law. Well, I can imagine, well, if there is a particle traveling in magnetic field, I mean, if I take a look at the symmetry of this arrangement, I can recognize that the force has to be either inward or outward. I mean, it has to be away from the wire or toward the wire, which makes a conclusion that, I mean, let's say that I pick that it's toward the wire. And indeed, in this configuration, it would be toward the wire. If I marked it the other way, I will just get a minus sign after the derivation, which would mean that the force which you marked is in the opposite direction. All right. So I picked actually from those two. I picked the one which makes every term positive. Including the force is really attractive in this configuration. Well, if magnetic force is in this direction while the particle moves this direction, well, we can conclude what would be the direction of magnetic field. Let me remind you that the directions are related by right-hand rule. And it comes from the definition of magnetic field. Magnetic force is supposed to be equal to the charge of the particle multiplied by its velocity multiplied by magnetic field using vector product. So if the charge of a particle is positive, it means that the direction of magnetic force is consistent with the direction of the vector product. All right. Velocity is the first factor. So I will align my hand with the direction of velocity. Well, now when I bend my fingers in the direction of magnetic field, the thumb is supposed to show me the direction of magnetic force. Well, it means that magnetic field must be in this direction. All right. And along, I can recognize that everywhere along this line, if I imagine a line concentric with the wire, so again from rotational symmetry, I can conclude that everywhere along this this line, this is a circle. So everywhere along this circle, magnetic field will be tangent to that circle, and the magnitude of magnetic field will be the same. Well, in this case, it will be easy to calculate that linear integral over the Amperian loop, because now notice that this line, which we just imagine, we don't have to make a material loop like from a wire. We just have to imagine a line. All right, so let's now erase what is not needed and use Ampere-Maxwell's law. According to that law, we have to calculate linear integral of the magnetic field. So here we have scalar product of magnetic field vector and a segment vector, differential segment vector. We have to divide this line into tiny pieces. To each piece we have to assign a segment vector. And I remind you that segment vector is assigned in such a way that its magnitude is equal to the length of the segment, and the orientation is along the path. In principle, I could assign this segment vector two ways. I can orient it clockwise or counterclockwise. Well, it will be easier if I calculate it counterclockwise, because then the angle between magnetic field and segment vector is going to be 0. Right, so this is my selection for the segment vector, and when I calculate it, the scalar product will have magnitude of the first vector, which is magnetic field strength, magnitude of the second vector, the segment vector, which will give me the length of a differential fragment of that loop, times cosine of the angle between them. And if they are parallel, angle is 0 degrees, cosine of 0 is 1, so I don't have this 1 over here. Now, this is a differential length, so really I can pick length as the variable of integration and make my mind about the integrals. And let me remind, why don't we actually recall the three factors which we have three facts which we have to remember when we set up the limits. Well, we have to make sure that we include every piece. All right? We include every piece only once, and we do not include pieces which are outside of the integrated path or whatever we integrate over. So since we pick here the length of the arc, if I start from any point, let's say from this point, to which I will assign s equals 0, so the lowest value for s, then the highest value for s will be full circumference of the circle, which means 2 pi times radius of that circle, or in other words, distance from the wire to the point at which I'm trying to determine the magnetic field vector. I already decided, from symmetry we concluded what is the direction, so we have now to determine only its strength. All right, now it's easy to integrate here, because from symmetry I could also recognize that magnetic field strength is the same along the path, so I can take it in front of the integral, and this integral will give me circumference of the circle. So the left-hand side of the Ampere-Maxwell equation gives me such an expression: circumference of the circle multiplied by magnetic field strength. And according to that law, it is supposed to be proportional to the total current flowing through the surface spanned by that loop. So we have to now, it's related to the current flowing through this surface. And what's the proportionality coefficient? Permeability of free space. So on the left-hand side, now I have to write permeability of free space multiplied by the current flowing through this surface. Now, how much current, or what is the current flowing through this surface? What is the value of the current flowing through this surface, through this big surface? Let's see how much current flows through this side, through a surface of this size over here. How much in this configuration here? None. Right. There is no current flowing. The only current which flows through this surface, well, it's a current flowing through this cross-sectional surface of the wire, which means this is the current flowing through this entire surface. It is flowing through the small surface, and it is flowing through the entire surface. So I can write that it's permeability of free space multiplied by the current flowing through this surface. Well, so now I can make a conclusion that the magnetic field strength produced by the wire at a point distanced from the wire by this distance r is equal to permeability of free space times the value of the current divided by 2 pi times distance from the wire. And the direction is, well, consistent with the right-hand rule. And actually, how about if we learn, I mean, in principle, we could repeat this, this analysis with a vector product, but if we have two quantities, like yesterday, for example, how we related rate of change of, let's say flux with the electric field in Faraday's law. With just one, I mean, we related those two quantities using right-hand rule, not three quantities like we do for vector product, but just two quantities. The same way, for example, magnetic moment of a loop. If I have a loop, how about here? Let's say that this is a loop of wire and current flows this way. What will be the direction of magnetic moment of this loop? Well, I told you to align fingers, 4 fingers with the direction of the current, and the thumb shows the direction of magnetic moment. So if current, for example, flows this way, I align fingers with 4 fingers with the current. The thumb shows the direction of magnetic moment. Now, when we were relating flux with electric field vectors, so let's say if I consider a loop like this. So if I consider electric field in this direction, then I would have to relate flux in this direction, following the right-hand rule. Now, have we also used this one in other configuration? I don't recall. Oh yes, well, in Ampere-Maxwell Law, it was also, if I consider current that way, then I have to consider a magnetic field this way, along a loop. Here it's the same case. If I would have to align current with the thumb, and magnetic field should be aligned with the 4 fingers. So 4 fingers should be aligned with the magnetic field, and so if I calculate magnetic field in this direction, I have to consider current in this direction, following the right-hand rule. Now, just to exercise this, why don't we assume that? I mean, how about if we think that current? It isn't true, obviously, but let's because it's not a constant current. Oh no, but I know. Let's consider instant that the current in those lamps flows to the right, to your right. I want you now to align your hand with the direction of magnetic field produced by that lamp when the current flows in the lamp in that direction. Go ahead, work on it. Now make sure to use right hand. This is left hand, right? Okay, so start using right hand. And at your location now. Yeah, because, yeah, I see that a lot of you now shows the direction that way. Well, it's kind of okay, but you are only at one point of that circle. So don't show it that way or this way. Just determine the direction at your location. Yes. So, for example, if I consider this point, and indeed I align my hand like that, it means that at this location, magnetic field is kind of inward. Yeah. Over here, it will be perpendicular to the screen. Over here, it's going to be to your right. Over here, I recognize it will be toward us. Over there, it will be to the left. Yeah, so at your location, I just want you to stretch your hand to show the direction of magnetic field. Actually, you will immediately see also the distribution. I mean, when you do it right, you will see the distribution of magnetic field produced by that lamp throughout the entire room when we determine properly the directions. So go ahead and align your hands in the direction of the magnetic field at your location. Go ahead. You have it wrong. You have it wrong too. Okay. Owen is on the right track. However, he still cannot stretch his hand along that direction. It's still curved. Okay. Now, Kyle, you have it right. Now, determine it at your location. All right. Yes. So indeed, you should. If we align thumb with the direction of the current, indeed. I mean, since you're sitting this way, you should have it this way, right? Which means that magnetic field line is a circle, right? And oriented that way. So now you have to imagine where you sit on the circle. So for example, where you sit on the circle? Just at the bottom, correct? So magnetic field at your location will be straight forward. Okay, Mike, how about you? Slightly up. Okay, Andrew? What? No. It will be just horizontal, like his, right? You sit also, I mean, or even slightly downward. All right, now, Oscar, how about you? Will be down, okay, and Sam? Not back. Down, and even more than for Oscar, right? Now, how about if we all now stretch the hands along the direction of magnetic field and then look at the others so that you can see what is the distribution, and I will do it too. And guys over there also stretch. Kevin, you are doing it. You are not aligning it right. I mean, you are aligning right hand properly, but you still have to determine what is the direction. Yeah? So at your location, not just the entire circle. Yeah, so over here, how about if I move now? Yeah, I will move. I will walk underneath, and I will be changing it. So if I move this way, it doesn't change. Now, as I move over here, it gets more and more horizontal. If I'm right below the lamp, magnetic field is horizontal, and if I move over here, it's getting more and more down. Over here, it's probably in this direction. All right. We will have one more example of this, how to, I mean, the problem with Gauss's law, and actually it was true for both electric field and magnetic field. Think for what kind of objects we were able to determine electric field vector. Can you recall for what objects we derived electric field vector using Gauss's law? I mean, here is Ampere-Maxwell, but using Maxwell equations. So for what what objects we derived expression for electric field vector using Maxwell equations? For a particle, correct, for a particle. For what else? Yes, Oscar? Do you remember? Not an arbitrary Gaussian, Gaussian surface was used to derive an expression. Well, we did this also for a sphere. This was one of the homework problems. We derived it for a infinite plane, and I'm not sure if we did this problem or not, but you can also for uniformly charged rod. It's easy to use Maxwell's equations to derive those expressions if the objects have high symmetry. Now notice also that here rod, this wire has high symmetry. Now I have here long wire. Really, the derivation is for infinitely long wire. This expression is, I mean, if I take an arbitrary piece of wire about this long and connect it through the leads, magnetic field at this location will be just approximately equal. I mean, magnetic field strength will be approximately equal to this expression, although it is okay to use, as long as the distance from the wire is considered to be small with the length of the wire. You can think about that wire that is infinite. But I cannot. Can I borrow this pen? Can I not? I cannot, for example, use this formula if I connect this end to one end of power supply and this end to another terminal of power supply. I cannot use this formula to determine magnetic field at Madumira's location by using this formula, because now I cannot say that that one can consider it as an infinitely long wire. I can use this formula if I want to calculate magnetic field at this location in the vicinity. Probably about this far. And the closer to the wire, the more accurate is this formula. I mean, this is actually how engineering works. I mean, in engineering and physics too, all the formulas are approximations, and you have to be aware to what extent you approximate. You will have certain tolerances which you can which you cannot exceed. All right. Now, if the shape of the wire is complicated, then in a similar way, like for example, for a complicated object, when we try to determine electric field vector, we couldn't determine it from Gauss's law. How did we do that? How did we calculate electric field vector produced by an arbitrarily shaped object and on top of it with a non-uniform charge distribution? Well, we had to divide the object into tiny pieces. For each piece, we calculated electric field produced at a particular location using Coulomb's law, and then added that, or integrated it over the object. So in other words, we had to integrate Coulomb's law over the object to determine the electric field at a particular location. Well, Biot-Savart Law does the same thing for magnetic field. We are not going to derive Biot-Savart Law. Therefore, I want you just to memorize it. First of all, comprehend it, and then memorize it. So let's say that I have an arbitrarily shaped wire, and I'm interested at the magnetic field at a particular location. Biot-Savart Law says that the contribution to magnetic field, how about if I mark it, from a differential segment of that wire is equal to permeability of free space divided by 4 pi multiplied by product of current and segment vector. So I have to multiply current flowing in the wire by the segment vector, and we have to, because again, segment vector can be oriented 2 ways. We should select, if in the Biot-Savart law, we should select the direction of the segment vector to be consistent with the conventional current, or at least current. So if I mark current flowing upward here, then vector ds should be also upward. Now I have to multiply product of current and segment vector using vector product with a unit vector from the segment toward the considered point. So how about if I mark the vector r, and this vector, that hat over here, not an arrow, but the hat indicates that it's a unit vector in the same direction as vector r. And then r without an arrow or anything represents what? What, Owen? Distance, correct. What distance? I mean, formally, it means magnitude of vector r. My magnitude of vector r, Owen is right, is equal to the distance from the segment to the considered point. All right. I want now, I mean, I'm not going to click now to mark this magnetic field produced by the segment. I want you now to work with each other and determine what will be the direction of magnetic field vector. And actually, you can use two things. You can relate indeed current with the magnetic field like we did a moment ago, or you can look at this vector product. From both cases, you can determine the direction of magnetic field vector. So let's start with considering current like in a straight piece of wire. So current is in this direction, which means that I would have to align my thumb with the direction of the current. Well, which means that the line will be oriented that way. So at this location, magnetic field will be sticking out like this. If I look now at this vector product, I will align first my hand with the direction of the first vector, so with the direction of ds. Now I have to rotate my hand until I'm able to bend my fingers in the direction of vector r, unit vector r, and the thumb shows the direction of the force, magnetic contribution to the magnetic field vector. Now recognize that this is just magnetic field produced by that tiny fragment. So if I want now to find out magnetic field produced by the entire wire, I would have to add them. And how about if we do it? Let's try to find magnetic field produced by infinite straight wire. So I'll take a wire like this, and I will use Biot-Savart law to find magnetic field at this location. The distance of this point from the wire, let's say that the distance of this point from the wire is r, which means that this plane over here marked by the circle is perpendicular to the wire. I mean, so, all right. So let me take now the segment and find out what is the contribution of this segment, and then I will think what to choose for the variable of integration, so that we can add contributions of magnetic field vector. So let's say that the location of this point is such that the vector, position vector of the point with respect to this segment makes angle theta with the wire. Now using right-hand rule, and it doesn't matter which way, I can align my finger with the direction of the current, and the four fingers will show me the direction of magnetic field. Or I can use vector fact that in Biot-Savart law I have vector product. So IDS is this direction. Now I have to turn my hand in such a way that I'm able to turn it in the direction of vector r, and the thumb shows the direction of magnetic field produced by that segment. All right, let's say that now position of this, I will identify position of this segment by measuring the distance from this point. So this is the point where the plane, this plane crosses the wire, which means that this angle is a right angle here. Because this plane was perpendicular to the wire. So here I have right triangle like that. I will use the fact that it is a right triangle. All right. Now, in order to find out magnetic field, I will introduce coordinate system and think about all components. And actually, I'll pick the coordinate system in a convenient way, because now look that every segment of the wire will produce magnetic field in the y direction, which means that the only non-zero component of the magnetic field in this coordinate system is y component, which means that y component is going to be equal at the same time at the strength of the magnetic field. So let us calculate this y component of this magnetic field, which happens to be also the magnitude of this vector dB, of the magnetic field produced by the segment. All right, so according to Biot-Savart law, I have to take permeability of free space and divide it by 4 pi, take a vector product of segment vector and the unit vector from the segment to the considered point, and multiply it by the current flowing in the wire, and finally divide it by the distance from the segment to the point of interest. All right, the rest is actually math. So how can I simplify this expression? Permeability of free space is a positive number, 4 is positive number, pi is positive number, and these are just constants. I can take it out. Now, all segments in a wire are connected in series, so I can recognize that current is also independent of the segment. So practically in this expression, it's also a constant, and consistently, I mean, all right, so I can take out in front permeability of free space divided by 4 pi and current. Absolute value of square of the distance is equal to square of the distance. Now I have to find magnitude of this vector product. Now, how do we find magnitude of a vector product? We take magnitude of the first vector, multiply by magnitude of the second vector, and multiply by sine of the angle between them. All right, so let's do it. Magnitude of the segment vector is equal to the length of the segment, and I marked it as ds. And so ds is the length of this segment. All right, so I took magnitude of segment vector. Magnitude of the unit vector. How much is magnitude of unit vector? 1, correct. So I have 1, I didn't even mark that 1. And then I have to multiply it by the sine of the angle between vector ds and a unit vector. So it's this angle theta. All right, let's see now before we integrate, let's see what is constant and what is variable. And so I have already mentioned that, well, in front we have those 3 constants. Current is independent of the segment, so in the integral it is going to be constant. However, the remaining things, sine of theta, this s, and the distance from the segment to the point vary. Well, we have to make our mind to choose one of those as the variable of integration and express all remaining variables in terms of this particular variable. Well, since I have already ds over here, I'm going to use s as the variable of integration. So this r square is a square of the distance from the segment to the point. How is it related to the position of the segment? Well, I've said already that it's a right triangle here. So using Pythagorean theorem, I can write that, well, I recognize that r is the length of hypotenuse. So square of length of hypotenuse is equal to the sum of squares of lengths of the other two sides. So I have r squared because it's the length of this side, and s squared because it's square of the length of this side. All right, so we took care of r squared. Now I have to take care of sine of theta. Well, I use the same triangle and recognize that sine of that angle is length of the side opposite to the angle divided by the length of hypotenuse. So length of the side opposite to the angle is equal to the distance from the wire to the considered point, and length of hypotenuse is equal to the distance from the considered segment to the point of interest. All right, now let's simplify it more so I can recognize that this is square of the square root. So really I have, if I simplify the expression and recognize also that this distance is as independent of the segment, I grouped terms that way. So now I just have, in order to find magnetic field due to entire wire, I have to add contributions from all pieces. And I recognize that I calculate in principle y component, but because the magnetic field is in the direction of y component, it is also going to be magnetic field strength. I took out the constants, permeability of free space, 4 pi, current, and the distance from the wire to the point. The thing which remains, I mean this second factor remains in the integral. Now we have to make our mind about the limits of integration. Help me. From it? Madhumira, I think, can you shout? For S, right, yeah. S is the distance of the segment from this point, and this point was, well, perpendicular projection of the point of interest on the wire. So the largest and the smallest value of S. Well, let's say that the distance from here to here is 5 centimeters. What would be S? 5 centimeters, correct. Now, how about a point further? What number I will give for that? 5.5, for example. And what will be the largest number which I would have to use to identify the last piece in this wire, infinite straight wire? How much? Infinity. Correct. Yeah. So the largest value for S is infinity. What's the smallest value? Negative infinity. All right. Yeah. So we will have to integrate from negative infinity to infinity. Well, now we have to go back to calculus and help me, give me a hint. What should I use to calculate this integral? What would you suggest to calculate this integral? Yes, Vincent? The first fundamental theorem of calculus. Correct. So first I have to find indefinite integral of this function. What's the variable in this function? S. Very good. Correct. So indefinite integral, I mean, we use tables, right? So you don't have to use tricks which you learned in Calc 2 or which we are learning in Calculus 2. We just use the tables from the back of the book. And from that table, I found that indefinite integral of this function is this function. I have to plug in values infinity and minus infinity. For what variable? For what symbol? For S. Correct. well, it happens that actually we will have infinity over infinity. So you will have figure out how to calculate that. Oh no, actually it's actually not that complicated, yeah, because you can recognize that if you plug in infinity over here, r practically doesn't matter. So here you will have square root of s squared, right? So you will have absolute value of s, which will cancel with this s. Well, so if we, and this r, you will move this r over here, and this r with this r cancels. So we got that the magnetic field strength at this location is equal to permeability of free space multiplied by the current flowing in the wire divided by 2 pi times distance of the point of interest from the wire. And this equation, this expression should make us happy. Why? Because we saw this formula 2 slides before, right? Previously we used Ampere-Maxwell equation to derive this expression. Now we found it from Biot-Savart Law. All right. Now, let's say that we have 2 wires in which and current flows in both of them. Well, these 2 wires are going to interact magnetically. Now, why? If let's say that I look at this wire, just at this wire, and recognize that current flows there. Well, if current flows in this wire, it means that this wire produces magnetic field, right? Everywhere around it. So let's say what will be magnetic field produced by this wire at this location. Why don't you use right-hand rule to figure out what will be the direction of that magnetic field? So we'll have to align thumb with the current, and the fingers show the direction of magnetic field. Magnetic field is going to be up. Yeah, so here we have magnetic field produced by this wire. And here we have another wire with carrying current in it. And current is flowing in this wire. It means that there is a magnetic force exerted on this wire. Why don't we use right-hand rule to find out the direction of magnetic force? And so current flows this direction. Magnetic field is up, which means that the force is toward the other wire. Actually, I can do, let's see the other way. How this wire, what kind of force this wire exerts on this one. So let's start with this. What is the direction of magnetic field produced by this wire at this location? It will be down. Very good. Yeah, magnetic field is going to be down. Now, current is in this direction. So using right-hand rule, magnetic force exerted on this wire, but by this wire is going to be to the right, which actually confirms one of the fundamental laws of physics. Which one? Newton's second law, right? Newton's third law. If this wire exerts a force on that one exerts opposite force on the first one. All right, let's now evaluate the force. Actually, how about if I leave it for you as an exercise? Evaluate now, or find at least the magnitude of this force. Well, how would you do it? Well, you can, from the formulas for magnetic field produced by a wire, you can determine what is the value of magnetic field vector at this location. And then, taking this magnetic field and this current, you can find out magnetic force exerted on this wire. All right. So this will be all for today. We will end the lecture at this point.